Swayam Prabha. Digital India. Educated India.
Welcome to this course on Introduction to Robotics, where we'll be looking at, we'll be studying various issues which are basic to the study of robotics. Now, when you think about robotics or the word robot, what is the first thing that comes to your mind? Well, to some of you, it would be something like a mechanical arm. For some, it could be a toy. Some could be a helper, some kind of a mechanical slave, or it could be something which is a little devious and something which is could be dangerous. So, if you look at basically these pictures which are shown here, so these are various things that come to your mind if you look at if you hear the word robot. And the first thing that comes to your mind would probably be a mechanical kind of an arm which has mechanical linkages and which is used in the industries for doing works like welding, spot welding, and spray painting, pick and place applications, assembly, etc., etc. To some of us, the word robot would also mean mechanical toy, as shown in this slide, where you can see such toys which are readily available in supermarkets. So this is a mobile robot which has wheels, which has powered by a battery. It has, if you look at this figure, it has some kind of a sensor in front to check for obstacles. And if you see the top or what is inside, then essentially there is a microcontroller which is driving the full system, which is powered by a battery, a local power source. So this is also something that comes to our mind when we think about the word robot. The other could be a mechanism which is moving. Say, for example, this has linkages. It is connected by a motor here, and this is also a servo motor. There is a gripper at the end, and this moves in space to do some task. So these are things that come to our mind. So in this course, essentially, we are going to be studying about various aspects of robots, the very basics of it. The first would be the history of robotics. Where did robots come from? And what are robotics? Where did the word robot come from? Next is, as you would understand, that robots essentially move in space. So when they move in space, an arm moves in space to do a particular task. So we need some kind of basic mathematics, or what we call basic transformations, that correlate the end effector of the robot or the gripper of the robot with the task it is going to do. And that is how the robot controller works. So we'll have to look at some basic elementary transformations. Then forward and inverse kinematics. If it has to pick up an object, how would the robot arm go to that point, and after picking up the object, how would it plan its trajectory and come to another point and drop the object? So that is covered in forward and inverse kinematics. Then a robot moves by actuators, which are essentially motors, electrical powered motors, and the feedback comes from sensors. So we also have to look at sensors, actuators, and the full control is done by microcontrollers, which actually controls the end effector to go from one point to another point. And these microcontrollers are programmed using language, sometimes C# or some other kind of programming language. And then finally, we'll also have to look at robot programming languages. Now, there are some languages like Victor's assembly language, which is very specific for robot programming only, and these are used in the industry. So here we'll be looking at what is the structure of this language and how to use this language to program a robot for industrial applications. And towards the end of the course, what we'll look at is several experiments in robotics. So for example, we had looked at this very simple two-arm manipulator, which can move from one point to another point and do a task. It is controlled by a servo motor and then finally by some kind of a controller here. So if you were to make a robot yourself, a mobile arm, arm like this, a serial arm, which is going to pick up something from this point and put it in some other point, what are the basic things you need, like motors, controllers? How are you going to control it? Or if you're making a mobile robot like this, which is going to move on the ground and avoid obstacles using a sensor, an ultrasonic sensor, then what is it that you require or what is it that you need? So towards the end of this series of lectures, We have a number of experiments in robotics, and after doing the experiments in robotics, you would be able to make your own robot. Not an industrial robot, which is something like this, which is pretty expensive and complicated, but very simple robots like mobile robots which can move around, do particular tasks, or an arm like this which can go to some point and pick an object and drop an object. So that is basically what we are going to, the lectures will cover, and towards the last we are going to have experiments, and finally you should be able to make your own very simple kind of robot. So before starting any course, it is customary that we look at the basic origin of the course or the history of the course. So the word robot or robotics as a subject essentially belongs to the area or the subject of automation. So the larger subject is called automation or industrial automation, and robotics is a part of automation. And so the first thing that we need to know is, when we say automation, what do we mean, or what does the word automation imply? So automation essentially means replacing human muscular power. So you can have different kind of automation. For example, at home we can have home automation, in office we can have office automation, in industry we can have industrial automation. So in all these applications you see that essentially it is human muscular power which is being reduced in some form by using a machine or a mechanism. And interestingly, this business of automation has been going on for thousands of years. Okay, it is not that automation was suddenly invented someday by somebody. So if you look right from about 10,000 BC or more, human beings were essentially using different kind of tools. For example, we used stone tools, then we used iron tools, then copper tools, and these tools were used to make better tools. And the philosophy here in automation is tools making better tools. And this process of tools making better tools has been going on for thousands of years. As an example, in industries, we can say about NC machines. From NC machines we have CNC machines, then we have DNC machines, then we have SIM, in that order. So this process of automation has been going on for thousands of years. It is there even today, and tools are making better tools. Now if you look at the earliest automation, somewhere around 150 BC, of which records are there, such simple automation was there about 150 BC in Greece. This is the earliest example of a steam engine, and how this would work is essentially they would burn fire under a container of water, and this water would boil and produce steam, and the steam would come out from these two sides. One is here and the other is there, which will cause, because one of the nozzle is on this side, the other nozzle is on this side. So what would happen, there would be a moment about this axis, and this sphere will rotate. Now this is the earliest example of a steam engine, and if you look at the date, it is somewhere around 150 BC. And similar principles were used in automatic closing and opening of doors. For example, here this is another example called Heron's door, again 150 BC. And how this works is essentially they would burn fire on this container, and this fire would heat up the air inside the container, and the air pressure would increase. And as the air pressure increases inside this container, it is going to force the water, it will increase the pressure here and force this water down, and the water will flow into this pipe and go on to the other bucket which is suspended here. Now when the water level here increases, its weight increases, and because of which it will cause this pulley to rotate. Now if this pulley rotates, what would happen is this door would open. So this is again an example of doing a task without human muscular intervention, which is called automation. So when you burn the fire, the door would open. When you extinguish the fire, the door would close. And this is an example, the earliest example of automation. And if you look at the dates, it was very, very early, about 150 BC. Now as we progressed further, about 1980s, we saw the automatic creation of automatic dolls which could write, draw pictures, and these dolls are still there in several museums around the world. For example, the Robotics Museum in Nagoya in Japan still has some of these automatic dolls which can automatically draw pictures, serve tea, and the date is about 1780 AD. Now as we progressed further, about 1801 in France, this gentleman James was an inventor of textile machinery, and what he did is essentially he encoded the designs on textiles in the form of a punch card. Now how this punch card works is essentially there are holes or no holes. It is very similar to the OMR sheet that we use today. So in the OMR sheet, basically we make a bubble or we leave it blank. So it's essentially a 0 or a 1. And what he did is all the designs that were made in the textiles, he encoded in the form of a program. And this program was read by this punch card machine. And it basically consisted of holes or no holes, a series of holes and no holes. And the earlier computers were also the earlier NC machines, CNC machines were also run by punch card systems in which there were holes or no holes, and the machine essentially had a reader which could read this, and then the machine would operate automatically. So this timeline essentially shows that automation started off very long time ago. It progressed slowly, and we had very simple automation like moving engine, Heron's door, automatic dolls, then Joseph Jacquard textile machines in France. And as we move further, about 1904, in the year 1904, essentially the idea of transfer lines in which a car was assembled at different stations. And even today, if you go to any car assembly plant, whether it's Tata Motors or it's Maruti, essentially we see how cars are assembled. So the car would be mounted on a conveyor, and at different locations of the conveyor there would be human beings or there would be robots doing particular applications. So the car would move on the conveyor, and then it will come and stop at a particular station. The robot will do a task, or a human will do a task, and then the car will move on to the next station. So this idea of transfer line was essentially invented or developed by Henry Ford in the Ford Motor Company in US in 1904. And this is used even today in most of the automobile companies. Now, just for history and historical interest, where did the word robot come from? So essentially in 1921, this drama writer Karl Kapek, so he wrote a drama or a play in which he said that in future there will be mechanical men replacing human beings to do dirty work in industries, as shown in this figure here, apparently taken from his drama. So he said that in future there would be mechanical men like this who are going to be doing the dirty job of human beings in industries, and he called them mechanical slaves. And this word robot essentially in the Czechoslovakian language means mechanical slave or mechanical man, and this is where the word robot came from. Now, of course, in 1921 there was no robots, but it's interesting that he could imagine that in future there will be robots, and he used this word. So he was the first person who used the word robots. Further, 1942, it was Isaac Asimov who first used the word robotics. And those of you who are interested in movies would know that there are a lot of movies today. I, Robot is there, The Future of Mankind is there, and Isaac Asimov is the first person who used the word robotics. And he also framed the 3 laws of robotics. It's again interesting that in 1942 there was no robots, and of course no robotics, but he could imagine that in future there would be robots, and this is the way it would be. He has written a lot of science fiction, interesting movies have been made out of it, and he's projected what things like robotics, AI would be even in the years 100 years from now. So for history's interest, for historical interest, the word robot came from here, and the word robotics is attributed to Isaac Asimov, 1942. Now, where did the robot actually come from? So essentially 1945, during the Second World War, they were making the atom bomb, and for the atom bomb project they had to handle radioactive material. Okay. And for handling this radioactive material, human beings couldn't handle it because it is radioactive. So they devised a device, mechanical 2 arms of this nature. So there would be a slave arm on one side, and on the other side you have a master arm. And there would be a lot of shielding between them and a lot of distance. For example, this would be kept in a distant room, and this would be kept at another room separated by a thick concrete wall. So the radiation from this side cannot come to this side. And how it is operated is essentially the operator would stand here, and he would hold the arm or the gripper and perform motions. For example, if he holds this and moves it on this side, what would happen is the wire rope tension on this cable would get the tension will change, and this tension will be transferred onto the other side. So if he pulls it on this side, this slave will also move on this side. Now, something to note here, essentially this is strictly a mechanical device. So there is no electronics here. The motion transmission is by wire rope and pulley, simply by changing the tension on either side. And so this is called the master slave manipulator, and it is also called the father of the robot. Now, In several atomic energy establishments, this is still used, because wherever they have to handle radioactive material, they have to operate at a distance, and this is called telemanipulator or manipulation at a distance. So, so in terms of history, this is attributed to the father of the robot, and this device, strictly mechanical device, is was developed around 1945. So now the question comes that what changed everything? What I mean by that is mechanical systems became electromechanical. A lot of electronics came in, programming came in, and we had sensors, we have actuators. So invention of what changed everything, that mechanical became electromechanical. So if you look at that, then we find that the invention of the transistor somewhere around 1948-49 gave rise to the concept of reprogram. So before this date, all devices were mechanical devices, and we could not reprogram a mechanical device. Once you have made the arm, you could not change the structure or its program, because there was no concept of reprogram. So with the invention of the transistor came the concept of reprogram, and you could program a mechanical device, and if you change the program, it will behave differently. And 1950 saw the first generation of the first robot called Shaky at Stanford University, which is shown here. So this is a mobile robot which has wheels, has very simple sensors in front, and can do very basic path planning. So 1950, invention of the first robot called Shaky. 1952 came George Dowell with his teach and playback devices for NC machines. And so NC machines and robots essentially came from the same technology, and that is the invention of the transistor. And so robotics is not very old. So 1950 to about 2000 or 2019 today, it has moved from here to here in about 60 years. And the progress has been very, very astounding. For example, this mobile robot can just move around and do obstacle avoidance, which is very, very simple. No complex computation. It doesn't have vision. It doesn't have other kind of sensors. Whereas this robot, which has about 54 degrees of freedom, it has very complex sensors. It has vision. It has speech recognition. It has other kind of sensors like gyros, inclination sensors, and it can walk. It can run. It can interact with humans. So 60 years to go from here to here is a very short time actually, but a lot of progress has been made, and robotics has moved from such simple devices to very complex devices like this. Now, so the first change, what I'm trying to emphasize here in this in today's lecture on history of robotics is what caused these changes. Now, the first thing that caused the change was the transistor, that we had a robot, the creation of the robot, and then it moved from here to here, right? So now, since 1948-49, we had what happened was the computer technology, the computers became more and more powerful. So in the earlier days, we had one program which was controlling one machine control unit. Here I mean one machine control unit means one computer, and it was controlling one machine tool. So either this is a NC machine or it's a robot, but it's one program, one machine, one computer, one machine. Now, as the computer got more powerful, what happened was we could have one computer which is controlling many machines. Okay. So we had a number of programs which are controlling one central computer, and the central computer is controlling several machines. So we have NC, then we have CNC. And as the computer got more and more powerful, about 1970s, what happened is the computer could now control not only one machine, but it could control different types of machines. For example, one computer controlling a machine tool, a machine work table, a machining device, a robot, parts carousel, and it could integrate all of this, do path planning, do motion planning, do scheduling. So essentially what I'm saying is that the computer is getting more powerful, and it is being able to control more number of machines. Now, so we have NC. So here we have NC machines. Then we have CNC. Then we had flexible manufacturing. And as the computer got even more powerful, we have computer integrated manufacturing, where the computer controls not only the robots and the mechanical devices, but it is also integrated with material handling, resource planning, etc. So the computer is more or less taking over the full manufacturing cycle, and this is called computer integrated manufacturing. Now, it's important to note here that industrial standards so far, or the types of industries, are classified into different groups, or depending on the timeline. So industry 1.0 is essentially earlier days before 1800, where most of the industries were run by water power or steam power. For example, industries during those days, 1970s, before 1700, the power source or the energy source was essentially water power or steam power, and these industries are basically what we call the first generation industries or industry 1.0. The second generation is where we had electricity, and this power source of driving the machines became electricity or electrical motors, and all the industries that are covered under industry 2.0 or 2.0 are essentially falling in this area where the driving element or the energy supply is basically electricity. So this is about before 1800, this is after 1800. Okay. This is about 1970. So this is industry 1.0, 2.0, then we have 3.0. Now in 3.0, it is essentially computers which are integrating or automating systems, and we call computer integrated manufacturing, computer aided manufacturing, computer and automation, or IT, what we call IT. So it's essentially we have machines, then we have computers, we have robots which are integrated, and essentially the computers are controlling the machines or automation. This is essentially industry 3.0, and it's about 1970s onwards. Now, so this is 1.0, 2.0, 3.0, and if you come to about 2005, we are in the fourth generation where we say industry 4.0. Now, what is the difference between this and this? Here also we have robots, we have automation, we have computers, but essentially we also have some other elements. Number one is we have a human in the loop, and plus we have some kind of a cyber physical system. So the difference between here and here is here we have a connection involving machines, humans, and very often AI. So these are what we call cyber physical systems, and this is where we are today. And this is from about 2005 onwards, and is likely to last for another at least 15 to 20 years more. So what is the fundamental difference between here and here is essentially here we have intelligent algorithms, sometimes called machine learning algorithms, and we have humans in the loop, and this is what makes this industry 3.0 different from 4.0, and this is where we are today. Now we use the word robot quite a few times in today's lecture, but so if we were to ask that what is a robot, or how would you define a robot? Now the interesting thing is nobody seems to agree. Now why nobody seems to agree is because all the companies who are making devices would like to call their device a robot. It sells better, it has more market value. So even people making wheelchairs would say that's a robot. People making vacuum cleaners will say theirs is a robot also. And students also like to say, whenever they do a project, or they always like to say that they are working on robotics and this is a robot also. So that is the reason why apparently nobody seems to agree on what should be called a robot. But in general, it's understood that to be called a robot, it should do some or all of the following. For example, the device or the system should move around, then it should sense and manipulate the environment, and it should display some kind of intelligent behavior. So if a system does one or all of this, then essentially we say that the system can be called a robot. Now moving around is very simple. A mobile robot moves around, a vacuum cleaner moves around by itself, so we can call it a robot. Sense and manipulate the environment, it must have some kind of sensory input output. For example, it should sense if there is an obstacle in front and avoid it. Okay. This also vacuum cleaners can do, a lot of wheelchairs can do, so we can call it a robot. Now display intelligent behavior is something which is a little tricky, that what is intelligent behavior? So in one sense, in the sense of what we use in robotics, it essentially means a system would be called intelligent if it can deal with unknown, unforeseen, or corrupted data. So for example, the sensors are not always perfect. Okay. So if sometimes you get data which is incorrect or which is corrupted, or data which is not there, then how would you deal with it? So intelligent behavior in that sense would mean ability to deal with unforeseen, unknown, or corrupted data. So by these three definitions, by these 3 points, we can classify a system into a robot or not a robot. Say for example, a CNC machine is a machine tool, it's not a robot. For the simple reason that a CNC machine does not move around, it does not sense and manipulate the environment, and it does not display any kind of intelligent behavior. So whenever we say, if somebody says this is a robot or that is a robot, we can very easily check that it satisfies either of this, and then decide whether it's a robot or it's not a robot. So from so with the invention of the transistor in 1950, we had till 1970 we had about 3 generations of robotics. Okay, so we had the first generation of robotics. These were very simple pick and place devices which no external sensors. So this is about 1950 to 1970. So the robot could be used in industrial applications for spot welding, spray painting, and it did not have any external sensors like vision system or other kind of sensors like ultrasonics to be able to interact with the environment. Now the second generation robots are from about 1970s onwards, and these have external sensors, for example vision, tactile, force torque, and these are for interaction with the environment. So the difference between here and here is essentially these robots can interact with the environment, whereas these robots cannot. And then from about 1990 onwards, we have third generation robots, which we sometimes call intelligent robots. They are made up of smart materials, sometimes they are biocompatible, etc. And these are called third generation robots, which are about 1990s onwards. And future robots is what we have and what we expect robotics to be. So there are several examples: biorobots, robots which are living inside the body, can be a part of the body, micro, nano, then cyborgs, androids, and so many others as in science fiction. So robotics is essentially divided into these 4 generations, and this is where we are now. Now the point of showing this slide essentially is that the first generation robots were created essentially because of the invention of the microcontroller or the transistor. Now what gave rise to this and what gave rise to this? That's what we are looking at here. So what gave rise to the second generation or the second revolution? So this we can call the first revolution in robotics caused by the transistor. The second revolution in robotics is essentially electronics became faster, smaller, and cheaper. And this is essentially because of the invention of VLSI, or very large scale integrated circuits, about 1970s, because of which all the electronics became smaller, faster, and cheaper, because you could embed a lot of the earlier vacuum tubes and you could replace a lot of the diodes, triodes with faster electronic devices, and they could be embedded in a single board. And this enabled the creation of external sensors such as vision cameras, advanced sensors like gyros, inclination sensors, force torque sensors, advanced controllers like microcontrollers, DSP. Then we had areas of speech recognition, then AI. So all these topics actually came up about 1970s, and that is essentially because electronics became smaller, faster, and cheaper. And this continued to about 1990s. So this is the second revolution of robotics. The third revolution, or the third generation, is essentially because of new materials. Now new materials, new actuators, interest in emulating biological design paradigms, and we had a lot of new areas like micro, nano robotics, vision, biorobotics, etc. Now it is interesting to note that smart materials based actuators and sensors gave the ability to make very, very small robots, say micro robots or nano robots, and they enabled actuation in different ways. For example, you could not make a DC motor which is very, very small. So if you take, this is an interesting example of what we call the size effect. So this is the essential control structure of a robot or an NC machine, where you have a controller, then there is an actuator which can be a DC motor, then we have a work table. Okay. In the case of an NC machine, it will be a work table or a tool, and in the case of a robot, it will be a it is going to be a link or an arm. And there is a feedback by means of an optical encoder, which is a feedback device, and essentially this is my closed loop control system. So the interesting part here is, if you want to make a very, very small robot, one way would be that we can shrink this, okay, make it small. And now how small is small? Say for example, an NC machine would be the size of a table, maybe 1 meter, at least a length of 1 meter. Now if you want to make a very small NC machine, a very small lathe machine, how small would it be? Maybe 10 millimeters. So one way would be that you take this 1 meter lathe and you shrink it in size, and you make it into 10 millimeters. Okay. The question is, would it still work? And essentially it is not going to work, because there are a lot of these components which cannot be shrunk. For example, if I make a very small DC motor, then what would happen is it will not give enough torque for cutting or for moving this work table. So there is a particular size to which you can shrink, and after that size you cannot shrink anymore. Now this is called the size effect. So if you want to make a very small device, a very small robot, then we have to use an actuator which is not a DC motor, and we have to make links which are small, which link can of course be made small. We have to use sensors which are also very, very small, right. So this DC motor cannot be shrunk, so we use what is called a smart actuator to replace a DC motor and produce the actuation. So as we go along, we'll see some examples of smart material based actuation. And the point being that essentially because of this size effect, okay, we are using this concept of smart materials and smart actuators came about 1990s, because we were trying to make robots which are very, very small, micro, nano and biocompatible robotics, and we could not make this using conventional DC motors and AC motors or conventional encoders. So this is the three generations of robotics. The first was essentially because of the transistor, the second was because of VLSI, the third is because of smart materials based actuation and sensing. Now the future of robotics essentially means the areas in which robotics is expected to grow in the next couple of years or the next decades. Number one is biorobotics, emulating biology, making micro and nano systems. Then exoskeletals are wearable devices, not only wearable robots but also wearable clothes, wearable sensors, wearable actuators. Neurorobotics, where the robot can actually be inside the body, okay, performing some function or a part of the body. Robotic drugs, nanorobots for curing disease, surgery. Then assistive rehabilitation robotics for example, like for stroke rehabilitation. Outer space and nuclear applications. Outer space and nuclear have traditionally been using robotics, and they are expected to use robotics to continue using robotics in the future also, because this is where human beings cannot go. So the only option is to use robots. Defense, soldier, autonomous armaments. So soldiers and autonomous armaments like drones are also becoming popular, because several of the countries do not want to put their soldier to harm. So one way is to use automatic devices like robots to perform dangerous operations. Replacement of body functions like artificial muscles. Then new terms which have come up: IoT, Internet of Things, cyber physical system. This all involves robotics and automation in some form. Okay. So this is the direction in which robotics has been going, and it is expected that at least in the next 10 to 20 years, these are the areas that are going to remain for research, for industry, etc. Now these are some examples of small. We said that robots are very small. How small is small? So this is an area which this is a figure showing a robot which is very small. How small? That it can go inside the bloodstream, and these are the red blood cells. So this robot is so small that it can go inside the blood cell and perform a particular task. For example, killing a particular virus or killing a particular cell. So it is so small that it can go inside the bloodstream itself. So we are already in that stage where robots are this small and they can be inserted into the body. Surgery. So this is another case where robots are expected to make a great impact is in surgery. For example, bypass surgery, where if you have an artery which is blocked, so essentially a robot can be inserted and the robot can go and drill and make a clearance of whatever is whatever is blocking the artery. So this is another area. We are already in this. We are already in the age where robots are this small, and for example, this is already being done in the case of placement of stents in the heart, where a small robot kind of device can be inserted, and then after the stent is placed, it can be taken out. So this is when we say small, we mean this small, or smaller than this. Some very strange kind of applications. A robot dentist, a robot for cleaning your teeth. Now these are very, very small robots which can do grinding on the teeth, and essentially this is apparently a very crazy idea, but then it has a lot of economic value, because if you go to a dentist, it's very expensive, whereas if a robot can do this task very easily, then it would be much, much cheaper. So there are actually companies which are making such robots for commercial application. A robotic haircut, again this is there in several parts of the world, where this is some kind of a cap where you have to wear the cap, and there are small blades inside which will cut your hair. Again, this is of economic interest, because an automated haircut is very, very cheap as compared to a human being cutting a hair. If not in India, but at least overseas, getting a haircut is a pretty expensive affair. This is something I talked about the smart materials based actuators and sensors. So this is a smart material which is an electroactive polymer, and you can change its shape like that of a snake, okay, and you can also control it. So this is an example of a smart materials based robotics where you can make very small devices. Now a mechanical linkage system cannot behave like this. So if you want to make something which is closer to biology, or you want to emulate biology, maybe what we need to do is to have sensors, actuators which are not the conventional DC motor, AC motors, but are made of smart materials. This is the example of a bird. Again, this is not a mechanical device, so it can behave like a bird, and this again does not have linkages. It is basically made of an electroactive polymer, and simply by giving it charge it can behave like a bird's wing. Then we have examples of exoskeletons, where these are robots which can be worn, and they can be used for enhancing the physical ability of a person. For example, if a person finds it difficult to walk up or walk down stairs because of paralysis, or the person has any kind of muscular degenerative disease, then this device can help you to walk up and down stairs. This device can help you to carry enhanced load. Such devices are also used for rehabilitation, automatic transport, where these are automatic buses which are already there in several parts of the world. These are driverless, and they are completely autonomous. So autonomous transport, brain computer interfaces. So this is another example of an interface or a man machine system in which instead of taking the input from a joystick where the person is moving, you can take the signal straight from the brain and then analyze the signal and then drive a device. So such devices are called brain computer interfaces, and they are already commercially available for very simple applications like playing games. So for example, in the car racing game, you can put on 2 electrodes and you can drive the car left, right simply by thinking left or right. And it is expected that in the next decade or more, these devices will be much more powerful, and will be having a better interface for communication. So for people who cannot speak or who cannot use their limbs, simply by thinking, the person would be able to actuate a device or be able to type. Automatic road tracking for autonomous cars. So the next generation of cars are likely to be electrical cars, and one step ahead is the autonomous cars, which do not have drivers or can drive by themselves. So this is also we can call it an autonomous car. We can also call it a robot, where there is no driver. It's a driverless car which can just move by itself from one point to another point. Driver tracking. Okay. So tracking the driver, whether he's asleep, whether he's paying attention to the door, paying attention to the road. So driver tracking is another area. Outer space has always been a favorite of robotics and automation. So space rovers like the lunar rovers which go to the lunar surface, or Mars rovers which go to Mars. So they have special structures, and they have a special kind of actuation and sensing for enabling them to move on rough terrain which is there on the moon or Mars. Then we have this robotic arm on the space shuttle, which is also a robotic arm which is actually helps astronauts to perform particular tasks in outer space. So outer space and defense has been there and is likely to be there for robotics in the next decades. Now very interestingly, ethics laws. For example, we always talk of industrial laws and industrial ethics, but now that robots are living with humans, and it is expected in Industry 4.0 that more and more robots and humans are going to perform tasks together. So what would be the laws that would govern the behavior of robots or humans? Okay. For example, if there is an accident and a robot injures a human, then who is responsible? Is it the robot responsible, or is the human responsible? So at present moment, there is no laws of that nature. And in the present industrial standard, the robot and the human are kept separately. So in fact, the robot is kept inside a cage and the human is outside. So the workspaces of the human and the robot are different. But in future, we are expected to be in the same workspace. So this is becoming very important. Ethics, laws, industrial laws, social laws. If a robot is staying in society, say for example, in several airports we already have robots which are there. Now what are the laws or what are the ethics that such robots should have? So this is a new area which involves not only engineers but also people in social sciences, in economics, and in other disciplines as well. So this basically gives us an introduction of the history of robotics, where robots came from, where it is going, what is the likely directions of what are the likely types of robots we are likely to see in the future, and so on. So after this we move on to the next more serious talk, that is, we have seen that robots essentially are made up of joints and they are connected by links. So this is the basic structure of a robotic system, in which we have this is a robotic arm. So this base is fixed, it does not move. These are joints and the two joints. So we have one joint here, one joint here, one joint here, and this joint is connected to the next joint by means of links, and at the end of it we have an end effector or a hand to perform some task. It is controlled by means of a computer or a controller, which can be a PC, it can be a microcontroller, or it can be a DSP, which is controlling this robot. So essentially this is the basic structure of a robot, and it consists of a controller. So we will look at microcontrollers as we go along. It contains joints, we will have to look at what are the kind of joints. Then it also has links, okay, and then there is an end effector. So what we need to look at next is we look at joints, what are the various kinds of joints which are there for robots. Then we look at when this robot moves in space, what is the relation between the end effector position and orientation with respect to the base of the robot. So if I want this robot to go from here to pick up something here, then essentially I must know what is the position orientation of the arm when it reaches there. That is how the controller works. So the next thing we look at is what are the different kind of joints. So the first kind of joint we have is called a prismatic joint, and as this is shown in this figure, this joint is like a rectangle. So this is a rectangular section or rectangular cross section, and there is another rectangle here. So this rectangle is inserted onto this base rectangle, and this joint is called a prismatic joint. It is also called a translating joint, and this joint can move up and down, but it cannot rotate. So we cannot rotate this joint about this axis, right. So this is called the axis, and the degree of freedom is it can translate, it can move up and down on this joint. So this part can move up and down along the inner rectangle, but it cannot rotate about the axis. Okay. So this is my axis, and the degree of freedom is a translating degree of freedom, and this is called 1 degree of freedom. So here when we say 1 degree of freedom or a degree of freedom, essentially it means that this is a what changes when this joint moves is this distance changes, and this is a prismatic degree of freedom. So this prismatic degree of freedom has 1 degree of freedom, and it is called a prismatic joint. The second degree of freedom, the second type of joint is what we call a revolute joint. So again, as this shown in this figure, so we have a cylindrical part which is mounted on the cylinder, and we have some kind of a stopper there. So the stopper is put so that this part cannot come down on this, otherwise it can freely slide down. Now this is the axis of the joint. Now in this joint, this cylinder can rotate about this axis. So either clockwise or anti-clockwise it can rotate about this axis, and so what would change when it rotates is essentially this variable angle theta, right. So this has degree of freedom 1, and the degree of freedom is theta, the angle which changes when this rotates, right. So this is a revolute joint, and the degree of freedom is 1, and the variable is theta. Now this is the third kind of joint, which is called a cylindrical joint. The essential difference between this joint and this one is that we have one cylinder which is mounted on this cylinder, okay, and there is no stopper here. So this cylinder can slide up and down, and it can also rotate, okay, about this axis. So this is the axis of the joint. This cylinder can go anti-clockwise or clockwise on this axis, and it can also slide up and down. So there are 2 degrees of freedom, or 2 variables. One is this distance, which can change, and number 2 is this angle, which when it is rotating this can also change. So a cylindrical joint has 2 degrees of freedom, a revolute joint has 1 degree of freedom. the fourth kind of joint is what is called a spherical joint or a ball and a socket joint. This is also called a universal joint, and this has 3 degrees of freedom. If you can imagine an axis system, so this is my x-axis, y-axis, and this is my z-axis. Then this can rotate about this. So this is a ball inserted inside a cup. So this ball can rotate in any direction. So it can rotate about this axis, it can rotate about this axis, and it can rotate about that axis. So it has 3 degrees of freedom, and this is called a spherical joint, prismatic joint, spherical joint, or universal joint, or ball and socket joint. Now, using this different joints, we make different kind of robots. So if you use different kind of joints, if I use a prismatic joint here, then the motion of this link will be of a particular kind. Now, if I use a revolute joint here, again this will move in a different way. So the kind of joints that are used on the robots will give a different kind of a motion ability to the robot. So the first thing that we need to look at is what kind of joint the robot has. So again, going back, this is a prismatic joint. It can only have a variable distance. This is a fixed distance, but the variable is the joint angle theta. This has a variable distance and a variable theta angle. This one has 3 variable angles, so it has 3 degrees of freedom. Now, if you were to ask the question that which joint system should we use, then an obvious answer would be this one. Why? Because this joint has the maximum degrees of freedom. So if you look into the human body, then our shoulder joint, our hip joint, our ankle joint, they are all ball and socket joints, right? But if you look at robots, then 99% robots are made up of revolute joints. They are of this kind of joints, right? So an interesting question here would be that this gives the maximum degrees of freedom, so why don't we use it? So if you think a little bit, this gives the maximum degrees of freedom, but actuation of this is a little problematic, because if I put a motor here, how is this joint going to move? I have to put a motor. So I put a motor here, I put another motor here, and I put another motor here. Now if I do that, then the shafts of the motors are intersecting at that point. Now you can well imagine that if we have 3 motors and the shafts are intersecting, then what would happen is it will be one motor will start interacting with the other one. So we will not be able to control them. So in terms of control, this is not possible to control this joint using DC motors, and because of which we can make this joint, but it's extremely difficult to control. So thinking a little bit, thinking about this joint a little bit, in biological systems, we do not have motors, but we have linear actuators, which are muscles. So a motor and a linear actuator like a muscle works completely differently. In a linear actuator, for example, in our shoulder joint, it is basically actuated by the bicep and the triceps of the hand plus the shoulder muscles. Now the elbow is also actuated by the bicep and the tricep muscles. So how does the elbow joint work? If the biceps contract, the arm moves up. If the bicep relaxes, the arm moves down. So that is the way the spherical joints work in biological systems, which are actuated by linear actuators, which are basically muscles. Whereas in robots are actuated by motors, and motors are not linear actuators, but they are rotating actuators. So although this joint works in biological systems, it is extremely difficult to use this in a robotic system. So very rarely would you see a robot which has this kind of a joint. And 99% robots would be having revolute joints, essentially because each joint would be connected with a motor. So there would be a motor here which is going to actuate this joint, and each joint would have one motor with its own controller and sensor closed loop control. So we saw that robots can have different kind of joints, and based on the kind of joints they would have a different structure and they would move differently. And the joints also determine the degrees of freedom of the system. So here by degree of freedom I mean the degrees of freedom of each joint, and in total how many degrees of freedom the robot has. The robot will have that many degrees of freedom. Now before we proceed a little further, it would be interesting to note that how many degrees of freedom are required to do a task. For example, if we have a table, so let me draw a table here. So this is a table, and on the table, so these are the legs of the table, and on the table we have kept a part. So this is a rectangular small rectangular box that I have kept on the table. Now, I want to pick up this box. I want a robot to catch this box, pick it up, okay, and maybe take it up like that, take it like this, and then keep it here. Okay. So, the robot should pick up this, catch this object, pick it up, and then keep it here. Okay. So, to do this task, how many degrees of freedom are required? Now, if you think a little bit, how do we answer this question? That there is an object which is kept on a table, and we are required to catch it, pick it up, and put it here. Now, how many degrees of freedom would you? How many degrees of freedom should the robot have? So, essentially, how do we decide, or how do we solve this problem? Now, essentially, you should see we need to figure out that how many degrees of freedom are required to do this task, and how do we answer that? For example, this object is kept on this table. So, if I now say this is my x axis and this is my y axis, okay, and this is my z axis. So, if I say this is my x, y, and z axis, then this object is kept on the table means the CG of the object is placed on this table, which means that it could be at any point on this table. Now, what does that mean? It means the CG of this object could be here, it could be here, it could be here, it could be anywhere, right? And on this table, if it has to be anywhere, it needs 2 degrees of freedom. It will have an x coordinate and it will have a y coordinate on this table, right? So, we need 2 degrees of freedom just to keep it on. So, we need x and we need y just to put on table, okay, put on table. So, if you want to put on the table, then essentially we need 2 degrees of freedom, right. Now, the robot has to catch the object, maybe it will catch it here at this location and catch at that location, and then take it up. Okay. So, it has to move along the z direction. So, along the z direction it has to move up, down, move up or move down. Okay. So, the robot will catch the object and take it up along this order, then move it sideways. So, this is my z. So, 1 more degree of freedom for the z. Now, it has to move along x y again. So, x y is already accounted for here. So, it can move in this direction in x y, and it has to move down again, which is z. So, z up and z down is accounted for by z. So, so far just to catch this object and move it up like this, we need x, we need y, and we need z, which is 3 degrees of freedom. Now, if you think a little bit, if you want to catch this here and here, you also have to orient the fingers properly, which will mean that if I have a gripper, if I draw a gripper here, so this is my robot gripper which is catching. Okay, if you can imagine that this is the robot gripper which is catching. So, the 2 fingers are placed here and here, which means that there has to be 1 degree of freedom which can rotate, because if the orientation of the object, if I keep the object in some other orientation, so I kept it in a different orientation, I keep the object in this orientation now, okay, which is different from this orientation. Okay. So, what is also required is I should be able to have a degree of freedom about this axis, and hence I need 1 more degree of freedom, which is a variable which is the degree of freedom theta. So, now coming back to the question of how many degrees of freedom are required for simply picking up an object and putting it on another box on the table, we require 4 degrees of freedom. So, this is essentially most robots, the least you can have is a 4 degree of freedom system. So, I hope this example clarifies that when we say we want to do a task and I want a robot to do that task, the first question that we need to ask is how many degrees of freedom are required to do this task, and the minimum is 4. Now, if you want to keep the object in at an angle, for example, I want to keep the object like this now. So, there is an angle there. So, the object has been kept at an angle now. Okay. So, there is an angle here, right, on the table. So, if we have an angle here, then I have to add 1 more degree of freedom, which will be this angle. Right. Now, if I want to keep at some other angle, then I need to along another axis, then I have to add 1 more degree of freedom. So, the minimum is 4. If you want this angle, then it is 5. If you want 1 more angle here, then it is 6. So, essentially robots, the minimum you can have is 4 degrees of freedom to catch an object and place it somewhere. And if you want to include all the degrees of freedom of the object, then it is 6. So, normally we have 4, 5 degrees of freedom or 6 degrees of freedom, depending on the task that is required. Now, so this answers the question of how many degrees of freedom that are required and what are the kind of joints that we have. So, now robots can be made up of, so if you are designing a robot, or you want to buy a robot, then how many degrees of freedom it should have is first answered from here, that what is the task you want to do. And then the next question comes that what is the type of joint you are going to put. Now, depending on the kind of joint you are going to put, the robot will have a different structure. For example, this is a robot which is made up of prismatic joints. Okay. So, this robot has 4 degrees of freedom. This is the side view and this is the top view. So, we can see here that in the side view, this is 1 degree of freedom. If you can imagine, this is a prismatic joint. Prismatic joint can only move in a straight line. So, this is 1, it can move in this straight line. This is the second one which can move in this straight line, and in the top view this is the third which can move in this straight line, or this is 1, that is 2, and that is 3. Either way, it's the same, right. Now, this robot can move in 3-dimensional space because the prismatic joints are going to move. Now, what is the area inside which the robot can position its end effector? We have to find out, because the task has to be inside the work volume. So, this area inside which, or the volume inside which the robot can position its end effector is called the work volume. So, for every robot, depending on the size, depending on the structure of the joint, the shape and size of the work volume would be different. Now, how do we draw the work volume of a robot? So, let us look at this particular case. This is called a Cartesian robot because it has 3 prismatic joints. So, this one has 3 prismatic joints, and the variables are variable is a distance, variable distance. Now, how do we proceed with drawing? So, first what we do is we see what is the range of this robot from here to here. So, this robot has a degree of freedom here. So, it is here. Now, when it moves from this point. So, when it is here, it moves from one end to the other end. So, what do we get is a straight line. So, this joint can move in a straight line here, right. So, we get what we get is a straight line. Next, this joint can move up and down. So, it is like this straight line can move from here to here. So, the straight line, when it is sweeping down and comes from here to here, what we get is this area, right. So, it is a square or a rectangle depending on the dimensions or the lengths of this and that. So, from the side view, what the work volume looks like is a square or a rectangle. Now, in the top view, if you can imagine, we are looking at this from the top direction. So, we are looking at it in the top view from here. So, what you can see is, what we essentially see is this line, right. So, this area is seen as a line in the top view, which is seen here. So, this is my line which is seen. Now, when this joint moves, it moves from here to there in a straight line. So, what would happen is, this straight line is getting pulled along this direction and it comes till here. So, this is the full area that the straight line sweeps, and it comes out like this. So, in the top view, what we have is a square or a rectangle. In the front view, in the side view, again we have a square or a rectangle which is like this. So, if I combine this side view and the top view, what are we going to get? So, what are we going to get will be so this is my side view, and in the top view it is something like this. Okay. So, what we are going to get is a cube or a cuboid, depending on the dimensions or depending on the lengths of the prismatic axis. Now, the robot can go any point inside this cube or cuboid, and this cube or cuboid is what we call the work volume. So, this cube or cuboid is basically called the of the 3 DOF degree of freedom prismatic Cartesian robot. Now, in robotics, it is basically written when we in terms of notations, what we write is, if there are 3 prismatic joints, we will basically say 3p, which indicates there are 3 prismatic joints, and this is also 3 degrees of freedom. So, this has 3 degrees of freedom, there are 3 prismatic joints, and the name of the robot is what we call a Cartesian robot. And what is important here is the shape of the work volume, which looks like this, and the robot end effector. The end effector means the gripper or the tool which is here at the end. This can go to any point inside the work volume. Okay. So, this is the work volume of a 3 degree of freedom Cartesian robot. Now, if we have a different joint structure, obviously we are going to have a different work volume. So, the second robot that we are going to look at is what is called a cylindrical robot. Now, a cylindrical robot essentially has one revolute joint. Now, this is from the top and this is from the side view. In the side view, we have two prismatic joints like in the previous case. This joint can move front and back here, and in this joint this joint can move up and down in that direction. So, the side view will be exactly same as in the previous case, where this joint can move from here to here. So, it generates a straight line. Now, this joint can move from there to here. So, this straight line is swept downwards and it comes here. So, what we get is this square or a rectangle depending on the dimensions of the lengths of D3 and D2. Now, when we see from the top view, okay, the same one when we are looking from the top view, what we are seeing is this is a rotating joint. So, this full length can move in that direction like this, or it can move like this. So, if you are seeing from the top view, then this area would look like a line, a straight line. So, this straight line is here, right at the center. Now, this straight line is being swept in this direction and it is being swept in this direction. So, the volume that we are going to get, sorry, the shape that we are going to get will be something like this. Okay. So, this is the shape of the work volume when we are looking at the top view. Now, when I combine this area along with this area, what is the shape that we are going to get? So, if you can imagine, this is the side view and this is the top view, then the shape that we are going to get will be something like this. So, this is my cylindrical shape, okay, and so this is going to be a hollow cylinder kind. Okay. So, if you can imagine, this is a hollow cylinder, the robot is sitting here and all area inside here the robot can go. Okay. So, these are areas where the robot can go at every point inside this volume, but it cannot go here. So, here it is not allowed to go, and these regions are called singular regions where the robot cannot go inside. So, if you can just go back here and see, when I combine this view and this view, what would happen is I would get a shape which will be a hollow cylinder, and the robot can go everywhere here inside this area, but it cannot go inside this area. This is not allowed for the robot. So, it is very important to know what is the shape of the robot, and again here it has two prismatic joints and it has one revolute joint. So, this is called a 2P 1R robot. This also has 3 degrees of freedom. So, today we end here and we will continue in the next lecture.